States of matter. Hitherto 5 states of matter are known, viz., solid, liquid, gas, plasma and Bose-Einstein condensate. Out of these solid, liquid and gas are commonly found while remaining 2 are found only under specific conditions. Interconversion of states of matter. These states are interconvertible. Melting point. This is the temperature at which a matter converts from its solid state to liquid state. It decreases in the presence of impurity. Boiling point. This is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. It increases in the presence of impurity and with rise in pressure. Boiling point of water is 100 degrees Celsius. Freezing point. At this temperature, a matter converts from its fluid state into solid state. Freezing point of water is 0 degrees Celsius. Evaporation. It is the process of conversion of a liquid into vapors at any temperature. Due to evaporation, water droplets appear on the outer surface of a glass containing ice-cold water. Water kept in earthen pot becomes cool during summer. Desert cooler. Cool better on a hot dry day. In short, the temperature and pressure at which all the 3 states of a substance can exist together in equilibrium is called triple point, e.g. ice, liquid water and water vapors can coexist. Ice water vapor at 0.0098 degrees Celsius and 4.58 millimeters. Plasma. It is a state of matter similar to gas in which a certain portion of the gaseous particles are ionized. Because of the average strength of the electrical forces, the plasma is neutral. It is commonly found in the universe. On Earth, plasma is naturally occurring in flames, lightnings and the auroras. Bose-Einstein condensate. A Bose-Einstein condensate is a gaseous superfluid phase formed by atoms cooled to temperature very near to absolute zero. This state was first predicted by Satyendra Nath Bose and Albert Einstein in 1924-25. Such first condensate was produced by Eric Cornell and Carl Wieman in 1995. It can be thought of as the opposite of a plasma. Factors deciding physical state of a substance. For gaseous state, forces of attraction less than thermal energy. For liquid state, forces of attraction thermal energy. For solid state, forces of attraction greater than thermal energy. Intermolecular forces. The forces of attraction existing among the molecules of a substance, gaseous, liquid or solid, are called intermolecular forces. Greater the intermolecular forces, higher is the melting and boiling point. Attractive intermolecular forces are known as van der Waals forces. The different types of intermolecular forces are briefly explained below. Dipole-dipole interactions. Dipole-dipole forces act between the molecules possessing permanent dipoles. The interaction is stronger than London forces and weaker than ion-ion interaction. Dipole-induced dipole forces. Dipole-induced dipole forces act between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Dispersion forces or London forces. Dispersion forces or London forces are present among nonpolar atoms and molecules, e.g., among the atoms or chlorine molecules. These are the weakest intermolecular forces. These forces increases with increase in number of electrons in molecules, increase in molecular size. The gaseous state. This is the simplest state of matter. Characteristics of this state of matter are: in gases, the intermolecular forces are weakest. Gases are highly compressible. Gases exert pressure equally in all directions. Gases have much lower density than the solids and liquids. The volume and the shape of gases are not fixed. Gases mix evenly and completely in all proportions without any mechanical aid. Measurable properties of gases. I. Mass it is expressed in gram or kilogram. E. Volume it is equal to the volume of the container and is expressed in terms of liter L, milliliter, milliliter, cubic centimeter, cm3, cubic meter m3, or cubic decimeter, dm3. 1 L equals 1000 milliliters equals 1000 centimeters 3 equals 1 dm3. 1 meter 3 equals 103 dm 3 equals 106 cm 3 equals 106 milliliters equals 103. Pressure. Gas pressure is measured with manometer and atmospheric pressure is measured by barometer. 1 Vatavaran equals 76 m of Hg equals 760 millimeters of Hg equals 760 torr. 1 Vatavaran equals 101.325 kilopascals equals 101,325 pascals equals 101.325 Newton meters minus 2 equals 1.01325 bars. 1 bar equals 105 pascals. Measurement of pressure of gas. I. Open-end manometer, PGA equals Puttom H. Closed-end manometer, PGA equals H. Where H is difference in the mercury levels in the two columns of density, T, of a gas. If temperature it is measured in Celsius scale, O, or in Kelvin scale, K. C. Unit of temperature is Kelvin, K. T. K equals T degree C joule 273. Standard temperature and pressure STP or NTP means 273.15 K or degree C temperature and 1 bar, i.e., exactly 105 Pascal pressure. At STP, molar volume of an ideal gas is 22.71098 L mole 1. Boyle's law. The volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. V1P or Vp equals K. K is a constant and its value depends on mass, temperature and nature of gas. P1 volt 1 equals P2 volts 2. Isotherms graphs of VVs P or PVVs P at constant temperature known as isotherms. IR distance at the sea level because it is compressed by the mass of above it. Charles' law. The volume of the given mass of a gas increases or decreases by 1 to 7/3 of its volume for each degree rise or fall of temperature respectively at constant pressure. Vt equals Vo 1 joule T 273 T constant P. Or the volume of a given mass of a gas is directly proportional to the absolute temperature at constant pressure. Vt at constant P V T equals constant or V1 T1 equals V2 T2. Absolute zero is the theoretically possible temperature at which the volume of the gas becomes zero. It is equal to 0 degree C at 273.15 K. Isobars. A graph of VVs T at constant pressure is known as isobar. Charles' law explains that gases expand on heating, so hot air is less dense than cold air. Gay-Lussac's law. The pressure of a given mass of gas increases or decreases by 1 to 7/3 of its pressure for each degree rise or fall of temperature respectively at constant volume. Pt equals 1 joule T 273 at constant V and N. Or the pressure of a given mass of a gas at constant volume is directly proportional to absolute temperature. Pt or P equals Kt or Pt equals K at constant V and N or P1 T1 equals P2 T2. Isocause. A graph of PVs T at constant volume is known as isochore. Avogadro's law. It states that equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. Mathematically, V in phi n at constant T and P, or Vn equals K. Molar gas volume: the volume of 1 mole of a gas, i.e., 224 Lat STP 0 degree C, 1 atom, I underscore S, known as molar gas volume. Ideal gas equation: V1P, T and N constant, Boyle's law. Vt, P and N constant, Charles' law. Vn, P and T constant, Avogadro's law. Vnut P, or PV nut, or PV equals nRT. This is known as ideal gas equation. R is known as universal gas constant. From the ideal gas equation, density D equals Pm RT, where m equals molecular mass. Ideal gas: the gas which obeys the equation PV equals nRT at every temperature and pressure range strictly is known as ideal gas. Real gases: since none of the gases present in universe strictly obey the equation PV equals nRT, hence they are known as real or non-ideal gases. Real gases behave ideally at low P and high T. Graham's law of diffusion. Under similar conditions of temperature and pressure, the rates of diffusion of gases are inversely proportional to the square root of their densities. Mathematically, R1 R2 equals D2 D1 equals. Diffusion is the tendency of gases to distribute itself uniformly throughout the available space, while effusion is the movement of gas through a small hole when it is subjected to pressure. Dalton's law of partial pressure. At constant temperature, the total pressure exerted by a mixture of non-reacting gases is the sum of partial pressures of different gases present in the mixture. P equals P1 jod P2 jod P3 jod. Partial pressure of a gas equals mole fraction of the gas total pressure. If N1, N2 and N3 are moles of non-reacting gases filled in a vessel of volume V at temperature T, the total pressure, P, is given by PV equals N1 jod N2 jod N3 RT. This is the equation of state of a gaseous mixture. Aqueous tension: it is the pressure exerted by water vapors at a particular temperature. It depends upon temperature. Pressure of a dry gas can be determined by Dalton's law. When a gas is collected over water, its observed pressure is equal to the sum of the pressure of dry gas and the pressure of water vapor, aqueous tension. Then, pressure of dry gas equals pressure of moist gas, aqueous tension. Kinetic theory of gases. Main assumptions of this theory are: 1. A gas consists of large number of small particles, called molecules. 2. Volume occupied by gas molecules is negligible as compared to the total volume of the gas. 3. There is continuous rapid random motion of gas molecules. The molecules collide with each other and with the walls of container. 4. The molecules are perfect elastic bodies and there is no loss of kinetic energy during collisions. 5. There are no attractive forces between the gaseous molecules. 6. The pressure exerted by a gas is due to the bombardment of gas molecules against the walls of the container. 7. The different molecules possess different velocities and hence, different energies. The average K is directly proportional to absolute temperature. K equals 3/2 RT. Average kinetic energy per molecule equals 3/2 cut. Here K is Boltzmann constant, it is gas constant per molecule. K equals RT equals 1.38 10 to 23 JK 1 mole 1. From the above postulates, the kinetic gas equation derived is PV equals 1/3 mund U2, where U equals root mean square velocity equals 3 RTM. Velocities of gas molecules. The different velocities possessed by gas molecules are: I. Most probable velocity alpha. It is the velocity possessed by maximum fraction of gas molecules at a particular temperature. Alpha equals to RTM. E. Average velocity V. This is the average of the different velocities of all the molecules. V equals 8 RT pi m. E. Root mean square velocity erms. It is the square root of the mean of the square of the different velocities of the molecules. Deviation from ideal behavior. At high pressure and low temperature, the gases deviate considerably from the ideal behavior. Deviation can be expressed in terms of compressibility factor Z, expressed as Z equals PV nRT. In case of ideal gas, PV equals nRT, Z equals 1. In case of real gas, PV nRT, Z1. Negative deviation in such case. Z less than 1, gas is more compressible. Positive deviation in such case. Z greater than 1, gas is less compressible. The factors affecting the deviation are I. Nature of the gas in general. The most easily liquefiable and highly soluble gases show larger deviation. E. Pressure. The deviation is more at high pressure. And N2 show negative deviation at low pressure and positive derivation at high pressure. E. Temperature. The deviation is more at low temperature in H2 and he always show positive deviations at 0 degree C. Cause of deviation from the ideal behavior. It is due to two faulty assumptions of kinetic theory of gases, particularly not valid at high pressure and low temperature. A. Volume occupied by the gas molecules is negligible as compared to the total volume of the gas. Though there are no attractive forces between the gas molecules. Van der Waals equation. After volume and pressure correction, Van der Waals obtained the following equation for n moles of a gas, where B equals excluded volume or co-volume equals 4 actual volume of gas molecules. A equals magnitude of attractive forces between gas molecules. The greater the value of A, the greater the strength of Van der Waals forces and greater is the ease with which a gas can be liquefied. Units for Van der Waals constant. Pressure correction. Limitation of Van der Waals equation. There is specific range of temperature and pressure to apply the equation. It deviates at very high pressure and very low temperature. Liquefaction of gases and critical points. The phenomenon of conversion of a gas into liquid is known as liquefaction. The liquefaction of a gas takes place when the intermolecular forces of attraction become so high that exist in the liquid. A gas can be liquefied by I. Increasing pressure, E. Decreasing temperature. I. Critical temperature Tc. It may be defined as the temperature above which no gas can be liquefied. Critical temperature offers 31.1 degrees C. Critical temperature Tc of some gases, ही 5.4 H2 33.2 N2 126.0 को 134.4 O2 154.3 CO2 3041 NH4 405.5 Tc equals 8827 Rb. E. Critical pressure Pc. At critical temperature, the pressure needed to liquefy a gas is known as critical pressure. Pc equals 827 B2. E. Critical volume Vc. The volume occupied by 1 mole of a gas at critical temperature and critical pressure is known as critical volume. Vc equals 3B. If Boyle's temperature Tb, temperature at which a real gas exhibits ideal behavior for considerable range of pressure is called Boyle's temperature. Tb equals a Br. Liquid state. If a substance is having melting point below room temperature and boiling point above room temperature, the substance is known as liquid. In liquid state, matter has definite shape and molecular motion is in between solids and gases. Properties of liquids. I. Vapor pressure. The pressure exerted by the vapors above the liquid surface when these are in equilibrium with the liquid at a given temperature is known as vapor pressure of liquid. The vapor pressure of a liquid depends on I. Nature of liquid. E. Temperature. Vapor pressure increases with increasing temperature. E. Boiling point. The temperature at which vapor pressure of liquids becomes equal to the atmospheric pressure is called boiling point. At 1 atmosphere pressure, boiling point is known as normal boiling point. At 1 bar pressure, boiling point is known as standard boiling point. Boiling point varies linearly with external pressure. E. Surface tension. It is the force acting per unit length perpendicular to the imaginary line drawn on the surface of liquid. It is denoted gamma gamma. SI unit, nanometer -1. Dimensions, kgs2. The magnitude of surface tension of a liquid depends on the attractive forces between the molecules. It is measured with the help of an apparatus called stalagmometer. Surface tension decreases as the temperature increases. Rise or fall of liquid in a capillary tube is due to surface tension. If viscosity. Viscosity is a measure of resistance to flow which arises due to friction between layers of fluid. When there is a regular gradation of velocity in passing from one layer to the next, it is called laminar flow. F equals ether adv does. Where F equals forces required to maintain the flow of layers. A equals area of contact. dv does equals velocity gradient. The change in velocity with distance. Ether is proportionality constant and is called coefficient of viscosity. Viscosity coefficient is the force when velocity gradient is unity and the area of contact is unit area. CGS unit of coefficient of viscosity is poise. SI unit of coefficient of viscosity is an S.